constructing maximally even tilings. We've had a little bit of background on that in recent days, so that's good. I can move through these first few slides a little bit quicker, but I still want to give the background in case anyone's missed it. Back in 1990, I think is when the mathematical music theory community really took an interest, when Dan Tudor-Musa published 4 articles in Perspectives of New Music. And since then, many of the people in this room and others outside this room have contributed to the theory of the structure and constructions of these tilings. Just in case anyone is unaware of what a rhythmic tiling is, I have a quick example of this here. We have a rhythmic motif that's translated to several starting positions. And the 2 important features here are that the parts are disjoint, meaning that they don't overlap at any point, and every beat is covered by one and only one note. So we can think of these as a set, or as a pair of 2 sets, the rhythmic motif and the set of translations of that rhythmic motif. Now, in the theory of rhythmic tiling, I think, unfortunately, we find that there aren't very many interesting ones in the sense that they all become most of them become very repetitive from a musical standpoint, from a mathematical standpoint, in the sense that they're periodic. We say that a rhythmic tiling is periodic if either the motif or the set of translations is a non-trivial, is equal to one of its non-trivial translations. So for example, in the previous slide, the 0, 5, 10 is the periodic part of this rhythmic canon. Now, aperiodic tilings do exist, but they're very rare, and they only exist for certain large values of n. And I think from a composer's perspective, it puts you in a little bit of an awkward position where you can choose to use some of these monotonous, very, I think, boring tilings and try to create interest in other ways. Or you can try to employ aperiodic tilings, which I think are quite interesting, but I think they probably surpass the audience's ability to process them because they're so long and complicated. So all of my research that I've done through these years has focused on bending the rules of tiling in various ways. And the main purpose of this talk is to bend the rules in such a way that I'm now going to allow holes in my tiling. I don't need to fill out every beat, and I call these partial tilings. And one thing to notice is that in this small example, we've already achieved something we couldn't do with full tilings, which is aperiodicity. This rhythmic motif is not periodic, modulo 13, and neither is the set of translation points. So that's a good sign that we're moving in an interesting direction. The other thing I want you to notice about this example is that I've given an example in which the notes and the rests are relatively evenly distributed. There's, for example, 4 notes and then a rest, 3 notes and a rest, and then 3 notes and then a rest. And I think that's somewhat important to retain kind of the feeling of tiling. In a full traditional rhythmic tiling, we have perfectly even rhythm with every single beat being covered. And so if we're going to bend the rules, let's try not to bend them too much. Let's try to retain that sense of evenness. And we can do that by referring to the theory that's been developed on maximally even sets. And so that's what I've confined myself to in this particular study is partial tilings that have a composite maximally even rhythm. And that's my goal, is to find constructions of these types of canons. Just in case anyone is unaware of the idea of maximally even sets, I have a quick example to show you the idea behind it. This rhythm with 10 notes and then 3 rests we would certainly not say that that's very even at all. We've clumped all of the notes together and then clumped all of the rest together. And then we can gradually do, little by little, get a little bit better. And then this is the maximally even. This is the best we can possibly do, given 10 notes in 13 beats. I will rely a little bit on the formal definition of maximally even sets, actually 2 of them. So I would want to point those out here. It was back in 1991 that Claude Meffet published a paper on maximally even sets and gave a couple different characterizations, and then others expanded on those characterizations. But the 2 that I'll rely on require that we talk about distance between 2 elements of the set in 2 different ways. We can give the usual moduli difference between 2 elements, or we can count the steps between 2 elements within a set. So for example, if I have a set 0, 2, 5, 9, 10, that's a 5-element subset. And I think of that as the subset modulo n. The distance between 2 and 9 is 7, but the number of steps from 2 to 9 is 1, 2. So being able to relate those 2 different kinds of distances together allows us to give a formal definition of maximal evenness. One of the equivalent conditions that tells us if a set is maximally even is this condition on the distance between any 2 elements. We say that we need the distance of the 2 elements to be close to what we expect it to be. This fraction is telling us what we would expect if the points were exactly distributed evenly. But of course, this fraction won't always come out to an integer, so we take its floor or ceiling, and if it comes out to one of those, if these distances always come out to one of those 2 values, then we say that the set is maximally even. Another nice characterization is that we have a direct construction of maximally even sets. We can take a similar type of fraction and just always take the floors of all of them. And any maximally even set is just going to be some kind of translation of that particular construction. All right, so back to tilings. There's an important distinction that I found that we need to make when we talk about partial tilings and maximally even tilings in particular, which is between what I call regular and irregular partial tilings. Some partial tilings, if we just remove all of the holes, retain the rhythmic imitation. You see here we've removed all the holes, and yes, the rhythm changed, but the fact that the rhythm is being imitated has been retained. We haven't broken the imitation. And the good thing about regular partial tilings is that they can be constructed from full tilings. We can start with the usual kind of tilings that we know a lot about, and by trial and error, or maybe by some other method that I discover in the future, we can figure out where we can put rests in that retains the imitation. On the other hand, there are partial tilings, such as this one, where if we drop all of the holes, the imitation is broken. See here the distance between the first and second note of part A is no longer the same as the distance between note 1 and note 2 of part B. So these are much harder to construct because we can't start from the usual tilings that we're familiar with. We have to find other ways to construct them each time. So I'm going to first focus on some of the theory around regular maximally even tilings, and then I'll move on to the irregular. There's some operations that are very, very nice on regular maximally even tilings. One is that we can expand them. We can drop a new rest in between each occupied beat and get a new partial tiling. And the nice thing about this is that not only does it preserve the imitation, the partial tiling aspect, but it also preserves the maximal evenness. And we can, of course, do this operation in the reverse direction if we have a large maximal even tiling, regular maximal even tiling, we take those rests out to reduce it down to a simpler, smaller form. Now, this has been done in various papers, maximal even rhythms before. I believe this next part hasn't been noticed, or at least as much, as far as I can tell, which is that with maximally even rhythms, we have short and long steps between consecutive notes, and we can swap them, and that retains the maximal even distribution. So here we have that same regular maximal even tiling, and we swap the long beats with the short beat. So this was a short beat, and now becomes a long beat. This was a long beat, and now becomes a short beat. And it gives us, quite a different looking tiling. This was a 10-beat pattern. This is now a 14-beat pattern. It's has a very different rhythmical structure, I think. So I think that's an interesting construction, and it retains the regularity, of course, too. So through these expanding, contracting, and swapping operations, we can define equivalence classes of regular maximums and minimums. Because of course there's an infinite number that we can keep expanding, but you don't get anything new or interesting out of continually expanding. So we want to think of these in equivalence classes, and through the contracting and swapping operations, we can reduce them down to a certain density, so that the beat to note ratio n over k is less than or equal to 1.5. And that should be pretty easy to see. You can do the contracting until you get this ratio down to less than 2. And then once it's less than 2, you might need to do that swapping operation to get it beneath 1.5. So that means that if we want to search for a complete list of representatives of all k-note regular maximal even tilings, all we need to do is start with all of the full tilings that we can find by various methods, and try applying, just by trial and error, all of the maximal even rhythms that we can that we have, which are unique up to rotation. So there's not that many of them, and only for n is less than or equal to 1.5 k. So it becomes a very much smaller problem to find these regular, or to be able to describe at least the equivalence classes of the regular maximal even tilings. So this is just an example of how we do that. We start with a full tiling, and we can say, well, let's try applying this maximal even rhythm. Does it work? No, because here the imitation doesn't hold. On the other hand, we can start with the same full tiling and try applying a different maximal even rhythm, and yes, this kind of works. So it's just a trial and error thing, but it goes pretty quickly, by computer especially. So next, move on to finding irregular maximal even tilings. These are the ones that can't be formed by simply expanding the full tilings that we know. And there's a useful necessary condition that I want to develop here that reduces this problem quite a bit. So this is a irregular maximal even tiling that I used on the previous slide. And I want to look at one particular instance of the irregularity here. And that is notes 1 and 2 in these two parts. They're 2 beats apart, but when we cut out the rest, we find that these two are now 1 beat apart, and these are 2. And this has to do, in terms of the maximally even rhythm, that has to do with the 2 ways of measuring distance between points in a maximally even set. We have 0 and 2, these 2 values, and 3 and 5, these 2 values, having the same distance, but differing in the number of steps. And so now we need to look at what made that situation possible, that we could have pairs that differ in the same in the distance, but different number of steps. So we recall one of the definitions of maximally even sets, which is that the distance should lie within this small set, floor, ceiling, what the expected value would be. And look at the particular possibilities we have for modulo n, quarter 10. For a single step could have a distance of 1 or 2. A double step could have a difference of 2 or 3. A triple step could have a distance of 3, 4, and so on. So the thing that made this this problem possible is right here, this intersection of the 2. Remember, it was that this problem exactly is what happened, where we had a distance of 2 in common, but they came from 2 different step lengths. So it's this this intersection that's the problem. Now, fortunately, this doesn't happen if we have the number of beats being large compared to A. For example, we make the n 23 instead of 13, and do the same computation. A single step has to have length of 2 or 3. A double step has to have length of 4 or 5, and so on. These are disjoint sets, so there's no way we're ever going to get that breaking of the imitation. If two notes in the tiling are 4 beats apart, they can't come from two different step values. So now we need to talk about when exactly does that happen. Well, it can be shown with some number theory that those sets that we've been looking at are only not pairwise disjoint if and only if the n value is less than or equal to 2 times k minus their GCD. So that gives us a necessary condition on the existence of irregular maximally even tilings, which is that inequality, which is really useful because if we want to find, for example, all 10 note irregular maximally even tilings, we don't need to look at every possible value of n. We only have to look at 11, 12, 13, 14, skip 15, and 16, 17, and we don't have to go on beyond that. It's a very much smaller problem. Now, based on my observations, I think there's actually a stronger condition. I think that 2 can be replaced by 1.5, but I haven't. Case by case, I can point out why it doesn't work. For example, I can point out why it doesn't work with n equals 16 or 17, but I haven't come up with a good general reason why this 1.5 should hold. But I hope to have that in the future. And this reduces things even more, of course. If I can prove this to be true, then all we would need to check is n equals 11, 12, 13. And that would be it. So that necessary condition that we found makes it feasible to search for all irregular maximally even tilings of a fixed, relatively small number of notes just by brute force. And I've done that, and it works pretty well. But instead, I want to look at some operations that turn regular maximally even tilings, or regular tilings anyway, into irregular ones. And the first one is unit multiplication, which in the context of full tilings, it's been noted that unit multiplication preserves tiling, but it's not useful in turning a periodic tiling into an aperiodic tiling. So it doesn't have the same significance as it has here, because what I'm going to show here is that unit multiplication does succeed in turning regular tilings into irregular ones. So it's a very useful operation. So first, I just want to show what unit multiplication means in case anyone's unclear about what it means in this context. Let's start with this irregular maximally even tiling we've been looking at. Multiply by some unit, modulo 13, and do the reordering. And what we find is, of course, that the partial tiling or the imitation is preserved. That's not surprising because that happens in full rhythmic tiling, in any kind of tiling. But what's interesting is that it doesn't preserve the maximal evenness. Here we have a group of 4, 4, and 2. And most usefully, it doesn't preserve regular and irregularity. This was an irregular maximal even tiling, but if you can imagine taking out those rests, you see there's still perfect imitation between the two parts. we have 4, 2, 5, 1, 3, 4, 2, 5, 1, 3, so on. So this bit, the fact that mutant multiplication does not preserve maximal evenness, makes things a little bit more challenging for us. But it's not that bad. This, on the other hand, is very, very helpful because it gives us a way to get to irregularity from a regular starting point. So this is a general method how we can try to produce irregular maximally even tilings from regular ones. We just start with given a certain value for k, start with all of the full k-note tilings that can be produced by various methods. And for each n that meets that necessary condition, which I hope I can change to 1.5, and each modulo n unit, each k-note n-beat maximally even rhythm, we can multiply that maximally even rhythm by the unit, which will probably, in a lot of cases, destroy the maximally evenness. But that's okay. We'll take this unit multiple of the maximally even set, apply that rhythm to the full tiling, see if it makes a partial tiling, and if it does, multiply by the inverse of that unit and see if we happen to get an irregular maximally even tiling. A lot of these will come out as we just kind of get back what we started with or something similar to what we started with. But in some cases, we will actually arrive at an irregular maximally even tiling at the end, which is useful. Based on my observations, which have gone up to k equals 24, I think, this works for, in order to produce every irregular maximally even tiling k-note n-beat maximally even tiling where the n and k are they have GCD1. They're relatively prime. So it's quite effective with those cases. But when the GC is greater than 1, sometimes it works, sometimes it doesn't. So we need another operation to use in those cases. Oh, I don't really want to go into this too much, but there are a couple of results that will be coming in my dissertation soon, and on the paper, that kind of help simplify the previous algorithm a little bit. This describes the units that preserve maximal evenness, and this describes the units that preserve regularity. So this kind of helps eliminate some redundancy, and this helps eliminate some cases where we know in advance it's going to turn a regular into a regular, so there's no point in trying those units. But I don't want to go too into that today. One of the techniques that has been used in full tilings in order to turn aperiodic tilings or compose aperiodic tilings into, or periodic tilings into aperiodic tilings is multiplexation. So I'm going to give a kind of a backwards example of how this works. This is an irregular maximally even tiling that can't be produced by the previous method. But if we separate out the even beats from the odd beats, we have these regular, quite simple maximally even tilings. So that's a really nice way to create these maximally even tilings. To start with regular maximally even tilings. The thing that makes this work is that the translation sets are the same. We have the translation set being 0, 1, 0, 1. Once you have those translation sets being the same, we can do this multiplexation technique and come up with a new maximally even tiling, which may or may not be regular. Again, it would have to be a trial and error. All of the maximally even tilings that have come across so far can be constructed by the methods I've talked about, but as I continue my work, I want to keep finding simple and efficient means of constructing maximally even tilings, especially the irregular ones, and work to prove that certain subsets of those techniques suffice to find everything, which, as far as I know, that hasn't been done for full tilings in terms of finding aperiodic tilings. There's no small subset that's been found that works. So I I'm guessing that's going to be a very long process to be working on this. I do want to talk about some of my related work because this is actually my passion. I'll come back to it when I'm done with my PhD thesis, which is about what I call G canons and S canons. G canons, they're based on the lone rulers, are very similar to tilings, except that they have one beat where all of the parts intersect. So I wanted to see if I could apply some of the same techniques that I've done with tilings to these types of things. And it turns out we can. We can talk about regular and irregular G canons the same way because there's full G canons, and we can try putting rests in maximally even ways and see if they come out as being a maximally even G canon. So here's an example of one of order 5. The interesting thing that I love about these G canons and S canons is that we can pick any melody we like and apply that melody in such a way that on the beat of intersection they're all in unison. Which I mean, it's not it shouldn't be surprising. It's just that one beat that needs to match up. But I like that we can create this this kind of, it still has the monophonic tiling structure that we expect in a tiling canon. So I wanted to play one of these. It'll start with the last part first, and then add the parts. This worked earlier. I get to come through. Let's see if this will plug through the speakers. What's that?
Do you play drums?
I play groups. Tried this out an hour ago. It worked.
Maybe you need to install your computer. This would be a distorted computer works. Maybe you can install the computer.
Start the
Yeah,
computer.
like
Let me see.
Meanwhile, you talk. You see them?
Okay, I'll just keep talking, and maybe afterwards I can come closer and hear. Do that. Okay. Anyway, a very closely related idea is seed sets. It turns out that if you know anything about how seed sets and lone rulers are, how they're defined in very similar ways, and they actually turned out to be equivalent to one another. Any seed set is a lone ruler, and then vice versa. The difference, but there's quite a difference in how we apply that to create a canon. This is an S canon based on the exact same melody, the exact same rhythm as the previous one, except that something very interesting happens when we apply the scene idea to it, which is that there's a bunch of intersections, there's a bunch of overlaps, But every time they overlap in unison. So we still have that monophonic texture that we had all along. And this has nothing to do with the particular melody that I showed. You can apply any melody you want here, and it still comes out in unison every single time. And I think they're just very beautiful. So maybe in a minute I can get this working. Now, unfortunately, this isn't maximally even. There's a very odd arrangement of the holes there. Full S cannons. This is fairly simple to show. Full S cannons only exist for orders 1 and 2. Just very small little examples. Here's a little one. So yeah, we could take this and we could put some rests in there and make it a larger regular S cannon, but it doesn't give you anything interesting. So our only hope then is maybe that there's some irregular S cannons out there. And yeah, I found them of order 3, but I don't remember how far I've searched. I've searched at least up to order 5 or 6 or something, and I haven't found anything beyond order 3. So it's kind of a downer slide to end on that I found so little. On the other hand, I think this is going to set up more investigation into, well, we can't come up with maximally even S cannons, but how close can we get with S cannons? That'll be another area of investigation for the future. That's it. I hope I can get some audio maybe in a few minutes. But
Are there any questions you really want feedback from?
Yeah, thank you very much, first of all, because it's nice to see that tiny cannons are still alive and doing good ahead.
Yeah.
And so, just a short comment, because you mentioned at the beginning these big Busa cannons, which are kind of complicated because the period is too long. Actually, it's not exactly true, because the surprise was that when we put together here, Thomas, Emmanuel, Frank, Carlos, Agon, we implemented the model, Busa models in open music, visual programming language. Then the catalog of solutions gave to the composers a lot of freedom. So every composer, a lot of composers, they actually perform pieces starting from the catalog in a spectral way, in a minimalistic way, it's really a stylistic model. It's totally open. So, my suggestion, I like very much the fact that we are now a little bit behind strict Busa canons, and we can discover much more freedom also in not perfectly canons or other kind of approximation of canons. But my point would be try to provide tools for composers. So try to put all these ideas in a environment which can be used by composers, because it changed everything. The fact that, for example, a lot of properties that we discovered with Emmanuel, they were kind of really inspired by the composer's use of this catalog of solutions. And so, the multiplication, for example, by a integer which is prime with a period, and the fact that preserve the canons. This is Tom Johnson intuition that was just manually doing operations. So all this would fit very well. I'm not doing publicity for open music visual programming language at Yerkam, but any software in which a composer can find already the algorithm. So no worry about the mathematics which is behind it. Sometimes it's very, very complicated, but you can take the freedom to explore, and then you will end up with really surely some new interesting results. Yeah.
I bet Emmanuel, I can ask him unison. I guess there's a nice, interesting special case from the Armand type scale, where Chopin's theory holds that you have a maximally even set of order n-1 and n+1, and the one is contained in the other. So, for example, the Black Keys, now you have 3 pentatonic scales on the piano, and 2 of them give irregular 2-voice canons, and 1 of them the regular I guess this is a general case.
You're talking about the fact that they're complementary?
Yes.
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 Yeah. So I've thought about that because then we could have one canon on one of the maximally even sets and another canon maximally even canon on the complementary set. And so I think that'd be an interesting thing to do from a compositional point of view. It doesn't work as interestingly in terms of when we do that, you pretty much have either a very boring complement, or the density is such that both are going to be regular maximum counts. And I'm always prone to that being interested in the irregular.
No, if you check the G major pentatonic and the F sharp major pentatonic, so this is an instance of an irregular. This is precisely an instance of an irregular maximum.
Oh, yes. No, okay, I know what you're talking about. Yeah. So you're talking about using that as a construction?
Yes.
Yeah.
Maybe it's not so interesting, but it's an instant.
Yeah.
Yeah.
I want to commend you on this research because I like the musical thinking, which is introducing holes and making the results more interesting, not just mathematically sound. It's something that appeals to the audience. And I remember that Tom Johnson, who did a lot with times and they used in music, was very happy to have holes because you can have rests, and rest gives some impulse, some interesting events as we have seen in one of the previous conferences. Also, I wanted to ask you about studying the effect of a fine transform that you have done. It's not written in the paper, but it's in the presentation, so I'm very happy about that. And it reminds me of iterating the action of fine maps, and also this is something that Tom Johnson has studied. And the result, the orbits, form autosimilar melodies. And I remember that in some cases, some very few cases, these autosimilar orbits tie. So maybe you have to look at that because there might be some intersection between these constructions and the results of yours.
I'd really like to hear more about that later. Because I completely understand those not. Yes. Yes.
There is something that can happen when you're everything is really interesting. But like when you're composing, you can have this process like you can after a moment want to escape it. And I was thinking like what will give from cellular automata perspective the image of a canon, because all what you're showing you can span it to 0, 1 to the power of natural numbers, like represent it like this. What will give, for instance, low rapid automata which is doing addition like this to the tailing? Does it stay a tailing? And if it's like the maximum one, will it stay the maximum? This kind of question. And there is also another point, so that's the direction when you're. There is another point which is frustrating from a composition point of view. You need to take a limit with your value of the smallest unit. And this can make you mad because like you're like, I'm blocked with that limit. Why not doing R time canon? And all what you're doing right now, I think you can do it in R with different distance. That would be distance between, because I don't know which needs to be defined, and like I guess it would be interesting with shifts which are real numbers and distances between your rhythm which are also real numbers in seconds.
Yeah.
It would be fun to do that.
I think I understand what you're saying. I think that's somewhere I might need to go with the S canons, since I can't construct maximally even ones. I might need to. You're talking about taking rhythms in real numbers.
Yeah.
Yes.
In seconds.
Yes.
You're taking everything you want.
Yeah, I think that's a great idea, and I can see myself going there.
If you need help.
Okay. All right.
Okay, well, my first words is congratulations, because yesterday I was using Chronomorph. I wasn't aware of the existence of this kind of rhythm. As in the musical perspective, I think that they are really useful as a tool to a composer. the two main directions that I will take to use is the first one is to create an interesting group, which is very important to get a proper stance. An interesting group. Group. Yeah.
Groove.
Yeah.
What's the word? Groove.
Okay. So that thing, and also use it in a counterpoint fashion with different voices. So I showed it to another musician, and the response was like it was completely brutal. So congratulations.
Thank you. Yes.
So your definition or your example of where it's an irregular Mexican technique. Is that
Yes. Yeah. I mean,
I think it has something to do with it. I'll see it anyway from there. Yeah, something to say about that.
So you're
this is the closest I get to it. The definition is what you're talking about.
When you had the example of when like you had that it wasn't regular because like one of the steps clashed with another one, like you had one with 2 or 3 and then another one started with 3.
This is what you're talking about.
Yeah, it's not the slide that I'm talking about, but you had like the tuples with and you made 13, 30 and it was and you had 2, 3, 4, 5, 6, 7.
Oh.
The slide before that where one of them so before that one. Yes, you have 2, 3, 3, 4, right? So that means that it's irregular.
Yeah.
That's a necessary condition, right?
These are potentials for irregularity.
Yeah.
So we could have. I mean, we do have the regular maximally even tilings. 13 beat, 10 note maximally even tilings. But this is what gives us the potential for irregularity.
Okay, so you can't have irregularity without that.
And the
You can have that without
the possible stronger condition, necessary condition I was talking about, I think it's going to have to do with how many possibilities there are. Because if there's only one, I don't think that's enough. I think you have to have more than one of these intersections. But
that jumped out at me because that's like well-formed sets. Maximally even sets are a subset of well-formed sets, well-formed words. Maximally even sets are well-formed, and the instance of that is in Carrie's work is known as a contradiction in well-formed words. So it might be worth looking into his research in sameness and coherence in well-formed sets to look for more information on when you get those irregularities, because it might have something to do with that, considering that's a particular instance. He's got a bunch of theorems of when that can appear, but then I didn't realize that wasn't necessary, wasn't sufficient for irregularity, but there could be something there.
yeah. Thank you. I would, if possible, I would like to demonstrate this. This is my only opportunity to share this kind of thing in person. But if it works, it'll be quick. There we go. So what you'll hear is these parts, it works musically best to start with the last entry. That way each new entry has got a head start on the previous ones. So you'll hear the last part enter and then the other parts in reverse order join. Same melody, same rhythm. And there you can hear the non-evenness. There's a lot more irregularity in how the notes and the rest are distributed. Yes?
I just realized that I would deal like here rendering with the continuous interpolation of pitch, just like metastasis. You would have the unisons.
Oh, yes.
in there, so
Having just the scale running up. Yes, I've done that before. It's an interesting effect. And one other thing I'll mention, I do have a paper that I published a few years ago in the Journal of Music, where it turns out that these S canons actually interlock together pretty well. Well, an S canon with its retrograde interlock pretty well. So if you're interested in these, you might want to check out that. Thank you.
Okay, guys, and last presentation. We are already sad, but now we need to eat in 45 minutes. We are going to go to the bus with a shortcut. Okay, if you can not go to the bus, no matter what, right?